Today we are discussing the pyrethroids. Pyrethroids have utmost importance in agriculture as insecticides. To keep it straight, pyrethroids are the synthetic analogs of natural pyrethrins, and I think it's worthy to discuss pyrethrins before getting into the pyrethroids. And these pyrethhrins are the toxic extracts of pyrethrum, which is referred to the dried flower heads of a plant called Chrysanthemum cineretifolium. These pyrethroids are six different components which are formed by the combination of two acids and three alcohols. Now let us see how these pyrethroids are formed. As I aforementioned, the pyrethroids are formed by the combination of two acids and three alcohols. The acids are chrysanthemic acid and pyritric acid, and the alcohols are pyrethroidol, cineroidol, and jasmolol. Okay, the chrysanthemic acid in the combination of these three different alcohols will give three different components, and they are pyrethrin 1. Okay, the chrysanthemic acid in the combination of pyrethroidol will give pyrethrin 1, and with the combination of cineroidol we will get cinerin 1, and with the combination of jasmolol we will get jasmolin 1. Okay, so just like chrysanthemic acid, the pyritric acid also gives three different components in the combination of these three different alcohols, and they are pyrethrin 2, cinerin 2, and jasmolin 2. Okay, so first these three components together called the pyrethrins 1, and these three components together called pyrethrins 2. So the pyrethrin 1 and pyrethrin 2 together called the pyrethrins. Okay, so these six components are responsible for the toxic effects of the extracts of the pyrethrum. So this is the skeletal structure of pyrethrins, and here you can observe two alkyl groups, that is R and R1. So if R and R1 changes, which means the alkyl group changes, the resulting component also will get changes. So let us see how these six components have different alkyl groups, which is R and R1 groups. So these are six different alkyl attachments for these six different components. So this is how pyrethrins are formed. Okay, let me repeat it for you. So pyrethroids are six different components which are formed by the combination of two acids and three alcohols, and the acids are chrysanthemic acid and pyritric acid. Okay, chrysanthemic acid with the combination of these three different alcohols will give three different molecules, and they are pyrethrin 1, cinerin 1, and jasmolin 1, and these three components together called pyrethrins 1. Just like chrysanthemic acid, pyritric acid in the combination of these three different alcohols will give three different molecules, and they are pyrethrin 2, cinerin 2, and jasmolin 2. Okay, these three molecules together called pyrethrins 2. Okay, the pyrethrins 1 and pyrethrins 2 together called the pyrethrins, and these pyrethrins are the responsible for toxic effects of the extracts of pyrethrin. And these six components have different alkyl attachments, and they are described here. So this is the skeletal structure, and with the different alkyl groups. So this is how pyrethrins are formed. Okay, these pyrethrins or these pyrethrins found potent against wide range of insects, which includes aphids, thrips, jests, borers, and even against some beetles. Okay, often these pyrethrins are used in the combination of synergies like piperonil butoxide and sesamics in order to enhance their activity against the susceptible insects. Okay, and despite having promising insecticidal properties, these pyrethrins are not much popular in agriculture. So because these pyrethrins are very susceptible to direct light and air. Okay, so it was found that cyclopentenyl ring. Okay, here you can observe. So this is the cyclopentenyl ring. Okay, so this is cyclopentenyl ring. So this cyclopentenyl ring is responsible for photo-induced oxidative decomposition. So which means the molecules with this structure will be very susceptible to sunlight. So okay, and here comes our synthetic pyrethroids. So these synthetic pyrethroids are synthesized or designed by replacing these cyclopentenyl ring with more stable molecules or more stable attachments, and one such attachment is M-phenoxybenzyl alcohol. M-phenoxybenzyl alcohol, and let's see the structure. So this is M-phenoxybenzyl alcohol attached to our pyrethrins, and one of the examples for the synthetic pyrethroid which is designed or which is synthesized by replacing cyclopentenyl ring with M-phenoxybenzyl alcohol is biopyrethrin. So after replacing cyclopentenyl ring with M-phenoxybenzyl alcohol, it was found that this molecule is very stable in sunlight which compared to the natural pyrethrins. So after synthesizing these molecules, some other changes, some other includes are also happened to these structures, and one such change is adding or introducing alpha cyano group. So this is alpha cyano group. So one of the examples of synthetic pyrethroids which is synthesized with alpha cyano group is delta methrin. So based on the alpha cyano group, pyrethroids are distinguished or separated into two groups. They are alpha cyano group pyrethroids and non-alpha cyano group pyrethroids. Okay, so as I mentioned earlier, there are two different groups based on alpha cyano group, and they are alpha cyano group and non-alpha cyano group. So examples for alpha cyano group is delta methrin, cypermethrin, phenolate. Okay, so these are the examples for alpha cyano group pyrethroids and non-alpha cyano group pyrethroids. So all natural pyrethrins, alethrin, tetramethyl, etc. Okay, so these are the alpha cyano and non-alpha cyano group pyrethroids. So in general, pyrethroids shows negative temperature dependence. So negative temperature dependence. But in some cases, this alpha cyano group shows positive temperature dependence. So this is about alpha cyano and non-alpha cyano group pyrethroids. In the synthetic pyrethroids, alethrin was the first molecule to be synthesized and commercialized as pyrethroid. Okay, and this alethrin is considered as first generation pyrethroid. And this alethrin is found very effective as insecticide, and it is very stable than natural pyrethrins. So immediately after alethrin, some other molecules were also synthesized and commercialized, and some of them are bioalethrin, resmethrin, bioresmethrin, these components or these molecules are considered as second generation pyrethroids, and these second generation pyrethroids are found more effective and more stable to light than first generation pyrethroids. So immediately after second generation pyrethroids, the third generation pyrethroids were also introduced and commercialized, and the examples are cypermethrin, deltamethrin, phenpropythrin, and finally phenvaligate. So these third generation pyrethroids are considered one of the most used or one of the most utilized pyrethroids in agriculture against a wide range of insects. Okay, so this is about the first generation, second generation, or third generation pyrethroids, synthetic pyrethroids, which were commercialized and still being used in agriculture for against a different variety of insects in different crops. So now let us discuss the mode of action of pyrethroids. To distinguish between pyrethroids, both alpha cyano group pyrethroids and non-alpha cyano group pyrethroids act similarly at the nervous system to delay the closure of sodium channels. But to say more precisely, alpha cyano group pyrethroids prolong the closure of sodium channels at more extent than non-alpha cyano group pyrethroids, which means these alpha cyano group pyrethroids are more potent than these non-alpha cyano group pyrethroids. Apart from acting on the sodium channel of the nervous system, these alpha cyano group pyrethroids can also act on the GABA receptor. So this is how pyrethroids act on the nervous system and cause lethal effects in the susceptible insects.